Josdan. I'm one of the executive co-directors of Pittsburgh Quantum Institute. Today we have Dr. Pedram Roushan with us here at PQI. Welcome, Pedram.
Thank you.
Pedram is one of the alumni of University of Pittsburgh. He was an undergraduate student here at Pitt. After he finished his PhD in Dr. Yazdani's group at University of Princeton, then he continued as a postdoctoral fellow at Dr. Martinez's group at UC Santa Barbara. And currently he's working at Google as quantum electronic scientist, right? Welcome again.
Thank you. Thanks for having me.
How was the feeling coming back 2 years later to Pittsburgh again and giving talks here?
I feel I feel like coming back home. You know, in the U.S. I have been living in several states and several places, being affiliated or working in several institutes. But now I felt really last night. I felt like I am home, and seeing my teachers, undergrad teachers. It felt home, being back home, and I felt the warmth that I felt when I was here. And also I know that these people know how little physics I know, so it was a mixed feeling, right? I was here when I had no knowledge of physics, and they were teaching me, and it's a great feeling. I received a lot from Pitt and the city.
I'm glad to hear that, actually. Let me take back you to those times and ask you about how was the feeling being an undergrad here at University of Pittsburgh?
I initially, I was a good student in high school and such, and I had some doubt that Pitt is a good place for me. So I came as a refugee. My aunt was living in this city, so I end up in this place. I had no money to go anywhere else. Practically no money to travel, even to explore, and I had to start something. So after one semester in community college, I got admitted here. But I always had feeling that, I could do much better. I had kind of looking down. I was arrogant and very young. But then gradually I start to appreciate what the place has to offer. So what do you need as an undergrad? You need a place that the courses are taught by people who care about you, and you need some research environment, so you start learning how to do research, or at least I didn't know how, and I needed that environment. So the classes and the teachers were really did what they were supposed to do, and I was double majoring in physics and mathematics, so I get connected to many people. The flexibility of the program was such that I could pick up courses that I didn't know. So if something was trivial or simple for me, I could just talk to advisors and get by and not take that course and waste my time. And then I worked in a lab for 3 years straight, and that was an amazing experience because I was someone who didn't know how to do anything, and someone gave me the benefit of the doubt. And then working with Walter Goldberg and Shalon Wu, at that time they were working closely together. I just heard that Walter is now really retiring after many years of being emeritus, and they gave me what I needed, and I wrote 2 papers with them essentially, with Shalom. So
I happen to see those papers. I will come to that point.
Okay, sure.
Yeah. What is the most essential things that you learned here at Pitt, which help you in your future career? I'm sure you learned many things, but if you want to say one thing,
I don't know. Hard work pays back. Hard work. I was really working hard, and I was very panicked about the whole future and dreams and everything I had when I came here. But the environment helped me to calm down and gradually see what I can do in the future. I think just being a very confused person on what is physics is, I have my thinking of what it is, how to do experiment and how to be in the lab. But then Shalom and the whole department helped me to form it, to something more meaningful and practical. I think the the vision that formed in here in my head of what does it take, you know. I mean, I'm not, maybe I never became a good experimentalist, but at least I saw good ones in here. Say, oh, that's how they are, and that was very valuable to me.
That's great. That's great. You mentioned that you did some research here, and actually, I think as an undergrad, you published your first papers here.
Yeah, I published with Shalon. There were 2 papers we published. Then me and him are the only authors.
Yeah. Do you remember what was it about?
Yeah, of course. It's on fluid dynamics. At that time, we Walter's postdocs or someone had this idea of how to make fluid flow of a fluid very, very thin. So you could make a film of maybe 5-6 inches wide, but a few micron in thickness. Very, very two-dimensional. And we had various techniques to perturb it and create vortices and study vortices. And that was the 2 papers about generation of these vortices, how these vortex, which are very compact, how they evolve in time, and what's the frequency of the vortex shedding. And yeah, there are 2 papers, one in PRL, one is Journal of Fluid Mechanics, I think it's called. But you know, at some point I felt that the only way to grad school is to have papers, because I'm competing with people who had more privilege than me, have participated, have gone to Ivy Leagues and others. Yeah. So I have to be, and I was working day and night. I remember some nights I was in Shalon's office up to midnight or 1 a.m. Well, Shalon managed to come back 8 a.m. the day after usually, but I was sleeping a bit longer. And we worked on this because I knew I have to get them published, but then when I get to grad school, I felt like, oh, all who are in grad school, my classmates probably have 5 papers or something. But apparently I had at least 200 times more than anyone else. Most of them had 1 or 0. Yeah. So I was driven and I was panicked, so it all led to publishing.
But eventually hard work paid off, and
yeah.
You ended up at Princeton.
Yeah,
right?
That was a good, yeah, I was happy at that, yeah, definitely.
And so you were working on 2D fluids.
Yeah.
And then as a PhD, you worked on topological materials.
Yes.
And then in your postdoc, quantum circuits.
Yes.
And now qubits.
Yes.
How did transition happen for you?
Serendipity, not really. So fluid dynamic, is there are lots of, or there are some big questions left, mainly on turbulence. But in US, fluid dynamic is usually get pushed away from physics department and goes to mechanical engineering or other departments. And there are not that many places have that research. And so I kind of moved away, and I want to do something else. It's willing to admit to it or not. There are trends. There are maybe I should not say the word fashions, or there are, you know, some research areas are less active and participated and are kind of. But it doesn't mean there's not big questions in there, or the questions are unimportant or answered. Yeah. But you know, it's just getting away from physics, and the mainstream of physics was going through quantum material, and now more toward quantum information. So that's how I gradually got into this. I chose Princeton, and then at Princeton I had several options, so I just went with one of these options. So I gradually got into, well, at that time, topological insulator was not even discovered, 2005.
Yeah.
And then 2007 or 8, my advisor were talking about them, and we had the chance of receiving samples from Bob Kava, and then in 2008 or 9 we did the first scanning tunneling microscopy study of them. But then I got to quantum circuits, and it was a period that I was doing something in between, and that's why John Martinez hired me, there was something that he was not fully expert on, and he felt I could bring that knowledge from my background, and so that's how it started. But that research didn't last long, maybe slightly more than a year, and then I joined his main effort on qubits, superconducting qubits. Yeah.
Like you were mentioning about like kind of passion in research. I feel like in these days topological materials are kind of passion. Like every paper that I read, I hear the word or I see the word topological.
Logical, yes.
Can you a little bit explain us what is like topological materials? Why they are
Well,
passion?
topology essentially for physicists means robustness. You know, you won't have some property if a material shows some property like a conductance or something. You want this property to be independent of details, and you know, however the material is made, you're talking about operations or measurements that are protected by topology, and that gives you some robustness. So you don't, it doesn't matter who made the sample or how it's made or if the temperature drifts a bit or whatnot, still you get the same property. And that is what stems the interest in this material, like integer quantum Hall being a topological property gives you a very precise conductance regardless of the details of the system. And I'm not sure if it's still used or was proposed to use as a unit of measuring conductance and measuring, you know, the charge of an electron, so or Planck's constant. So that's what attracts people to topology, and I fully understand why.
Yeah, and in fact, I think one of your most cited papers
is on topological issue. Yeah.
Yeah, you were mentioning about surface states, topological surface states.
Yes.
Can you tell us a little bit like how those surface states are created?
Well, let me give you an example of topology and then get back to it. The robustness people can think about when you have a ball, or the ball doesn't have any hole in it, right? If you start adding the local curvatures of it, if the ball is deflated or full spherical, it doesn't matter. If you add local curvatures, all the local curvatures, and integrate over the whole surface, you get a number which is independent of this shape, and it tells you essentially if the ball has a hole in it or not. So in that sense, so imagine you have a football, and irrespective of the details of it, you get this number. That's why this topology is interesting. The surface state is kind of analogous to this. Is you're asking about some curvature in some fancier space, momentum space, and it happened that some symmetries of the bands of certain material allows you to have states that are robust in the surface, and since it's coming from these symmetries, are going to be there forever without being worried about it. But the challenge of the material, at least when I left the field in 2011, was in being sure that your conduction is coming from the surface and not the bulk of the material.
Yeah.
So really you have a surface on top of an insulator, and that was a challenge back in the day.
Yeah. What is the main application on these materials?
Well, people are getting creative with that, but I would say, I guess a robust conduction channel, and also you can think about, playing with the shape and engineering, some making the scattering, you can control that, you can get some spin polarized currents, or some act as a filter that gives you certain electrons with certain spins and not with other spins. Or you can think about just the fact that it's a robust conduction channel, and you would know how much conduction you are getting.
Are they going to be used in the quantum computers or the qubits?
People probably propose that, but I would say I'm fine if there is no application in that case. People can propose, people can push on it, but I would say we have better candidates. And I mean, when I was doing it, I was not into making a device out of it. It was more to study the properties of it. And maybe in that sense it was good because we didn't try to uh, present it or think about it as something which is a very takes lots of stretch of imagination. It was a good match for what it was.
And currently you are working at Google. Can you a little bit tell us about like how is your work day?
How's my
like
work day?
at Google?
I think it would be less I never had the chance to be a professor somewhere, but I think it has less administrative thing, way less administrative, but some days it all goes to administrative tasks. Um, well, we have the unique chance to, as being a researcher or engineer. I think the name you mentioned in the beginning is quite flexible. It really, at some point, they gave me a title, and I was like, oh, I don't like this name or title. What is this job? They said, oh, you can change it to anything you like. So it's not about name and creating a hierarchy. It's really about getting the job done and focusing on the actual work. So so this good thing about Google is that I'm part of a very professional team. So if I get stuck, I can go and ask questions from people who are very experienced and have been in this, and the whole team is really experienced. I've had the state-of-the-art knowledge and information, and also I have the chance to work in the lab myself. You know, sometimes we have to balance with the incoming members of the team, and still we have certain grad students that I have to help with their task and their project, and just be sitting there and listen to their data and whatnot, and figure out the future directions and what
So
help.
you do have your own grad students as well?
Well, when we moved to Google in 2014, my postdoctoral advisor, who became my Google manager now, had, I don't know, maybe 10 or more grad students. Some of them graduated and left, some of them graduated and joined Google, some of them are still grad students. And I'm involved in helping them, not as an official advisor, but just, you know, helping, unofficially helping be sure. I mean, but everybody is helping someone in the lab, more junior, senior members helping the junior members. So sometimes goes to that kind of things. But some time goes to actually doing the experiment, you know, being in touching the system. And well, for now we are working on expanding the system, so lots of energy goes into purchasing and bringing parts and making fridge and wiring the fridge and getting the electronics and fabrication going. So I would say it's a very healthy balance, in a sense that, you know, you have the chance to work in the lab and not just report and apply for fundings and such. So in that sense, it's a very, very good environment. But on the other hand, we are given the freedom to present and communicate with the theorists and other people and collaborate after we have done our work of writing our patents and whatnot, and securing our publication and that kind of a standard industrial settings. But then we can openly talk about the works, of course, to certain level, not all the details, but in that sense, we are not closed institute, and that's very valuable to us.
That brings to my next question.
Sure.
Maybe, what are the biggest questions that you are trying to answer in these days?
You're right. Actually, the one person that works very close to me, we kind of drafted something together, and I keep asking him to actually publish that on archive. You know, the problems that we want to get help from experimental or theoretical community. We kind of have that list, and we want to publish it. You know, because one basic fundamental beliefs we have at Google is that getting a quantum computer, making a quantum computer, or advancing quantum technologies to the level that we can make a quantum computer is a very hard task. And we need collaboration across many disciplines and many people. The closed door policy of, like, let's lock ourselves up and then we do it ourselves, I think is very is not going to get anywhere. So that's the fundamental reason behind our collaboration. In particularly in my case, I think what we are trying to do is to make a bigger chip which has more qubits in it, and then be sure that the coherence, meaning the quantumness, the quantum features are preserved and not getting to limits that quantum mechanics is not, because we want to exploit the quantumness. And if your quantumness is gone by decoherence, by connecting to environment, by noise, by other defects, then we are not doing what theorist wants us to do, to implement the algorithm. Implementing an algorithm is quite meaningless at that time. That's one challenge, how to make it bigger and preserve quantumness. But then when you make something big, how you are controlling it? You have to think about these as puppets, and a puppet master who has to control all these at the same time, and is very exponentially sensitive in your motion of your pulses and synchronization of the pulses, size of the pulses, distortion of the pulses. So how do you do that? That's a big challenge. And if we could achieve both of these, then we are golden. Then we can do a computation that no one can do.
That's great. That's great. Yeah. Do you have any exciting recent results that you want to share with us?
Well, our work appeared in Science yesterday, or today, December 1st, I guess. Yesterday, last day of November. So that shows where we are, or where we were when we submitted the work about a year ago, 6 months ago. That's the state of the art in the terms of control. So we can control 9 qubits, and this is 6 months old. We can control 9 qubits simultaneously with high precision and preserve the quantumness. And that means you have to play with 17 knobs at the same time. So this, I need to have 17 fingers, and then you have to do something at the same time, and the motions have to be all very precisely controlled. So that's where we are now, and we are very proud of it. And in fact, we came up with a simple, very eye-catching and very simple to communicate example of it. We realized very old, interesting pattern of simulate the motion of electrons in a magnetic field. We show how our system can be used to do that. The spectrum of that would look like a butterfly, and people will know about it, but no one could see it before. So we say, look, if you could control this quantum system, this is an example. I'll be talking about it this afternoon, but it's in the press now, it's published. So we communicate that, look, is a very good example that I think people can go and read and see how we can basically demonstrate basic features of quantum mechanics and basic predictions based on quantum mechanics.
That's very nice. I was reading one of your papers in arXiv, and you were mentioning that you are months away for the demonstration of quantum supremacy.
Supremacy, yeah.
First of all, can you explain us a little bit
what's
quantum supremacy?
So very soon after inception of quantum mechanics, we realized that putting it to action and solving some problems in physics and chemistry are actually really hard. Yeah. Really hard, then become more quantified by being by the polynomial hierarchy of what hard it is. So it's actually is well understood how hard it is now, but still it's very hard. And then Feynman came and say, well, we can use quantum systems and control them to do quantum for us, to become a quantum engine for us. That started a race to make a quantum computer, essentially, and well, it started the efforts, and now it became a race. So the first idea, the first thing to demonstrate is to show that you can do a computation that no one else can do in a classical computer. And that is the first step. The computation could be like you know, it seems like you can give me a calculator and I can punch numbers in here, and I ask you, what did I multiply by what? And I can do it faster than you, okay? That there is no meaning to this computation, but I have to do it precisely, and I have to be able to do it with high fidelity. And it has to be a hard problem. So first we have to choose some problem which is complex. Second, we have to do it with high fidelity. So on archive, we put a work which shows how to do it and what problem to pick and how good we are at the moment. So quantum supremacy, meaning demonstrating, you know, I start from some state, and then I do an operation on it, and I measure, and then you check with your computer, and then I make it bigger chip, and I repeat it. Now you have to go to supercomputer, and then you have to borrow some computational power from some supercomputer somewhere, and eventually I would be able to add 1 qubit and continue my computation. It would not be very hard for me. It would be just linearly increasing in complexity for me of operation. And then what for you would be, you have to make the size of your quantum, your supercomputer bigger. If it takes 1 building now, somewhere in some basement of some building or somewhere, now you have to double the size. So at that point, I claim victory. But now you have to trust me that I did the computation correct. So there's all this subtlety into this business. But that's the idea behind quantum supremacy, to show a computation which is complex and we can do it with high fidelity. So I want to emphasize these 2 words of complexity and fidelity, which is kind of as this supremacy race is heating up, people have to always look for whoever claims this, that there is these 2 elements to it. Otherwise, I can throw something and say, hey, predict the perfect trajectory of it. If you cannot predict the perfect trajectory, you're not better than anyone else. You have to be able to predict that more precisely than anyone else. And also, it has to be a hard problem. You see, if I throw a ball, and you can use some very simple physics to explain it. You can be not very wise, and you can divide the ball into many tiny pieces and try to integrate the motion of each part, but you can think about it as a rigid body and just have 1 degree of freedom and work on it. So this example I'm using has some relation to some research work of some of our colleagues. But that problem is not solved because you chose to solve it in a hard way. The problem has to be genuinely hard. So I like whoever is watching to be careful about this, that there are these 2 requirements for claiming supremacy. How far we are for claiming supremacy, we are making the chip bigger. So the published work appeared in Science yesterday is on 9 qubits, that's a few months old. We have made bigger chips, and the good news is that it takes only 49 or 50 or some number of qubits to do something classically impossible. So we are working hard, and we are trying to get there. Yeah.
So we talk qubits a little bit. Maybe there are some audience
Sure.
that they don't know what is qubits. Can you tell us what is qubits?
Right. So in classical computers or classical bits, you do the processing by having units which can be in 2 different distinct positions. It could be occupied, unoccupied. It could be a switch. It could be on and off, or maybe it's you have an island. The magnetic field can be pointing 1 direction or can be magnetized in 1 direction or the other. And these 2 distinct positions allows you to store your information, your picture, or streaming anything in form of zeros and 1, and then convolve it and deconvolve it to communicate a signal. But that's fine, and it has some computational power of these zeros and 1 that you can use. But imagine you can be 0, 1, or both at the same time. And that gives you a huge advantage over classical computers. It's not mathematicians or computer scientists could get picky on this. I know it's not precisely this, but I think it's intuitive and it's okay to say it because many other people probably said it before me, that you can think about this as give you some parallel processing power. Because you are not only 0 or 1 and you are at both at the same time, so you can do some you are in many different states, many different configurations at the same time, and you can essentially do a computation in a parallel manner, that you are really checking all possibilities at the same time. This is a very rough analogy, and I'm sure mathematicians are not happy about it, but that's fine.
And I believe there are many ways to make this qubit.
Yes.
So what kind of way you are using at Google?
Right. So, right, there are many different ways to make a qubit. You can have a hydrogen atom, and then you can get the electron of it to be a spin one direction or another, and there you go, you have a qubit. You need a quantum system which has two states, and these two are distinguishable, and they're distinct enough, sorry. And then you can call one to be your 0 bit, the bit being in 0 state. The other one you can call the bit to be in 1 state. So there's no, there are many candidates. The way we do it is a bit maybe harder to communicate. It comes from something called Josephson Effect. And essentially, if you, maybe a simple way of saying it, is that if you have a superconducting, you can have supercurrents in it. But if you make superconducting in a loop, you can have supercurrents. But now if you open up a little bit into this loop, make a break and make a very tiny oxide layer or a very weak connection, now you have a Josephson junction. And the motion of going one way or the other is quantized into this loop, or and these states that we are using as our quantum states, being in certain currents into this loop, we are using as our.
So you are basically flowing current in one direction and in another direction.
That's one way of doing it. We are slightly different than that, but you can think about it that way.
What is the advantage of this way?
Well, advantage is that is a macroscopic phenomena, quantum physics at macroscopic scale. I have it in my backpack. I can show it to you later. That the quantum system you can see with your eye. A hydrogen atom you would have a hard time seeing.
Yeah.
But this one is big. You can see it is maybe 1 millimeter. A qubit is 0.5 millimeter across. So you can see it with your naked eyes. Okay, what's good about that? Well, I said that I have to control this like a puppet master. And if you have a hydrogen atom, good luck finding it and good luck controlling it. But if so big, you can bring, literally, you can bring wires to it. Wires take a little fancier shape. In here would be a strip of aluminum separated by carving into aluminum photolithography. But this allows you to control the state of the qubit. I think our progress have been really hinged on this property, that we can, because these are big objects, we can bring wires to them. And because the idea of Feynman, right, we remember, we are building on the vision of Richard Feynman, who said that, use quantum, but what was very implicit in this was that, look, you need to control one system to emulate the other one. The control takes wires. Where is the wires? How are you going to bring 5 wires to a so I think this is an advantage of it. And then it merged when you bring it out to more standard electronic and fabrication standard in quantum material science. But still you have to wait to see who makes the first. So I could be all wrong, but it has this advantage.
Hopefully you're not. So I'm also interested in kind of your personal research life. Do you have any interesting moment or exciting time, an aha moment that you want to share with us? That's something that you would never forget. I don't know, maybe your first paper is published.
Definitely, I do remember very vividly the moments we worked with Shalon, and many hours, and wherever we found we found how to interpret the Strahol Reynolds. I forgot even the names. The relation of frequency versus the Reynolds number relation. I do remember those moments. But also, I do remember the moments that I received a scholarship or fellowship at this very, or the paper got accepted. Now my heartbeat goes up every time I have a paper in review in a big journal. I do remember all those moments very vividly. Um, yes, yeah, it's hard to describe the moments that you discover something or your data really does. I can tell that it's just a bit overwhelming that you cannot sit quiet and you have to, you just can't sit. You just start walking or running or kicking something. In one case, that's what I did. So yeah.
Like you kicked something,
yeah.
you got excited, or it was the other way?
Both ways. At some point, I broke my toe because
you broke it.
Yeah, and my lab mates thought I'm crazy, or the doctor was trying to send me to some counseling, and I'm like, dude, this standard research.
What did you find at that time?
Oh, I set up for an experiment which was very long, and the software reset.
Oh God.
It was like 24 hours data, and in the middle of it, data got reset. So I got so angry that I kicked some chair and I broke my toe, and then it became a story that people use against me. But there was good moments too. I end up in kicking softer objects, so it didn't. But also I do remember the moments of rejection, and again you just get shut down, and it's very intense moment that why they're rejecting. Sometimes it's political rejection. You know, they just don't like somehow something about. But then sometimes it's decent physics rejection, and makes you think that what you have done, was that a good choice? What did you do? And I think a good physicist, a good life experience would be to make something out of those moments. I do remember those moments too, that, you know, I had to go for a walk for hours to get back to normal. It's such a, I don't know, surge of blood to your brain or something. You just shut down. But a bad person, a bad approach would be to blame people, saying, oh, they don't appreciate us, blame it on animosity. But a good approach would be say, well, maybe I did something wrong, and maybe I'm not doing the best, or I'm not doing it properly. And I think it worth focusing on both. Yeah.
What are your future plans?
I'm planning to control the states of the qubits in a large system. And that's that's going to fill up my very much life and day and night. And I think if we could control a state of these qubits over larger systems, maybe a few 10 or maybe a few hundred, we would be in a very good shape. And as I said, you know, I didn't say yet, 2012 or 13, we have 3 qubits, and then we got 9, and now we are making a slightly bigger chip. And it's not hard to imagine in the next few years we would have a few 10 or few hundred. And if I could demonstrate a good control over it, I would be very happy. And if it's really, really well done, then I get to figure out what to do next. But I think becoming a master of that would be a very, I don't want to think beyond that. It's just, that's very, very fulfilling at the moment to think about it.
That's nice. So that brings me to like kind of end of our conversation here. But I have one more question, one final question. It's not more like what you think about this. Like, if you wanted to say something to our student members.
Student members. Okay, yeah.
What would you say?
Yes. You see, quantum mechanics started in the early part of the last century. And it brought with it consequences that people like Einstein could never make peace with. It turned out Einstein was wrong when it comes to the EPR paradox. He really formulated his criticism of quantum mechanics in EPR, and he debated with Bohr for many years. This philosophical consequences that quantum mechanics brought really perplexed us for many years. And still, I don't think the problems are solved, or they are really lively and heatedly debated, and I think it should be. The entanglement, superposition, the probabilistic versus deterministic, these are very interesting problems. And with the work of John Bell, it came from the land of epistemology to experimental physics. This is beautiful. But then there is another thing started, another way that, look, you know, they call it shut up and calculate. It is a school of thought, meaning that, look, these are there, these questions, these philosophical conundrums are there. But we can use quantum mechanics. The last century was about birth of quantum mechanics, and then getting thinking about the philosophical, and then what does it mean? This century, I think that research and that questions and that discussion is alive and should be. But this century is the century of engineering quantum platforms. And we're trying to exploit and use quantum mechanics. As Feynman said, you know, nature is quantum, so we can use it. And it's interesting, in the early 1980s, he said, this is an interesting problem to simulate quantum system with quantum systems, because it's very, because it's hard. He knew it at that time. It's a hard problem. So I think this is a really flourishing and expanding field of quantum engineering and advancing quantum technologies. And I feel like this century would be very much focused on this. As you can see, now we are moving away from, not moving away, moving out from academic settings, because the work is getting bigger and it becoming more demanding financially and in terms of resources. So some aspects of it can be done in university settings, but big companies, Google, IBM, Intel, Microsoft, and other startups are looking into this and becoming very huge industry, rightfully so. And I feel like if people are not certain what to do with their undergrads and what they're start deciding, I feel like this century is the century of engineering quantum platforms.
Oh, that's great. Thank you very much.
Sure.
Thank you.
Thank you.
It was a pleasure to have you here at PQI.
Thank you. My pleasure.